Equations are all commonly used when we're doing highway drainage design. Starting with how we classify flow, a common classification method is based on whether the flow is steady and unsteady, or uniform or non-uniform. Those changes are typically defined with respect to time and space. So if the flow is changing, if the hydraulic conditions, the depth, the velocity, are changing with respect to time, we call that unsteady flow. If they are constant with respect to time, it's steady flow. In contrast, changes with respect to space, for example, as we move down the flume, if it's constant, if the depth and the velocity don't change, we call that uniform flow. But if the depth and the velocity are changing with respect to space, we call that non-uniform flow. Let's turn on the flume and we'll look at examples of those types of flow, and then we'll see how that affects some of the hydraulic calculations we do. The flow is basically steady because my pump is running at a constant discharge. And if I adjust the sluice gate a little bit just to knock the surface waves down coming out of the head box, certainly through the midsection of the flume here, we have what I would call uniform flow. So what you see here is steady uniform flow. If I were to oscillate this sluice gate now a little bit and create changes with respect to time, we have what's called unsteady flow. So getting back to my steady uniform flow condition, if I were to insert some stop logs at the end of the flume, I can create a steady, non-uniform flow. This is a special case of flow. We call it gradually varied flow because, well, the flow is varying gradually along the channel section. We'll talk more about that in a few minutes. So let's get back to the steady uniform flow condition. That's a very important condition because it's the underlying assumption of the Manning equation. We all learned about the Manning equation in our open channel flow class in college, or maybe our fluids class. And we probably, at the time, knew, I'm sure the professor emphasized that this is for steady uniform flow. The problem is we get out in the real world and we think, well, I've got an open channel flow problem. What's the equation I'm going to use? Oh yeah, I can use a Manning's equation, which says the discharge, Q, is equal to 1.49 divided by the Manning N times the flow area times the hydraulic radius to the 2/3 times the slope to the 1/2. So it's a very common, very often used equation for open channel flow. The most common application is we use Manning's equation not to determine the discharge, because that comes to us from our hydrology study. We do a hydrology study, we get a Q, and then we want to know, given that discharge, Q, what's happening in the channel? How deep is it? How fast is it moving? If I were to apply the Manning's equation, for example, to my flume, I know the discharge. This pump is running at about 0.05 CFS. I could measure the slope of the flume. I could look up a tabulated value for N value. The N value for plexiglass is about 0.009. Given that information, I could plug that all into Manning's and I could back calculate the depth of flow. And what depth would I get? I should get exactly the depth that we see on the flume if I'm in steady uniform flow. The Manning's equation, given good input for the discharge, the slope, and the N value, should predict exactly what my flume is now doing in steady uniform flow conditions. We call that depth the normal depth. When I was in college, at first I was a little confused. What does this mean, the normal depth? And it was really quite simple. It means it's the depth that the channel would normally flow at under steady uniform flow conditions. There's nothing magic about the term. It's what the channel would normally flow at, and so that's what we're getting right now. We're in steady uniform flow. The channel's normally flowing at this normal depth condition. But what happens if I change the hydraulic conditions? For example, if I put the stop logs in, and now I clearly have that steady, non-uniform flow condition. In fact, this is the gradually varied flow. And I did the same calculation. Well, the discharge hasn't changed. It's still about 0.05 CFS. I can measure the slope again. I can use the same n value, 0.009. And when I back calculate the depth of flow, I'm not going to get this gradually varied flow condition because this is not steady uniform flow. What I would actually get is what happens if I don't have the stop logs. I apply Manning's equation. The depth I'm going to get is this depth. And that's the dilemma that we face. When we're using Manning's equation, we have to be sure we're pretty close to a steady uniform flow condition. Because if we're not, the calculations we do will not reflect what's really happening on our project, particularly if there's something that's keeping the channel from doing what it would normally want to do. So, an important underlying assumption of Manning's that is often forgotten: we must have steady uniform flow. If we don't, a more complicated analysis, typically called the standard step method for gradually varied flow, and implemented by a computer program, for example, the Corps of Engineers HEC-RAS computer program does backwater surface profile calculations for gradually varied flow. Another type of flow that we can have is rapidly varied flow. And what I'll do is I'll stick my broad-crested weir into the flume to model what might happen if we had a bridge crossing with the abutment projecting into the channel. And in this case, you see the flow changing rapidly. Thus, we call it rapidly varied flow. This leads to another equation that we use quite often in open channel flow. It's called the continuity equation. The continuity equation is really just a restatement of something we all learned in physics, the conservation of mass. So if we have continuity in a hydraulic sense, then the discharge is constant, and that because of that, the continuity equation says that the discharge is equal to the velocity v times the area, the cross-sectional flow area. And more than that, under the continuity concept, says the product of the velocity and area at section 1 should equal the product of the velocity and area at section 2, and so forth, all the way down the channel. So we can illustrate that with a floating ball. When I put the ball into the channel, you'll notice that as it goes through this contraction at the bridge opening, it accelerates quite dramatically and exits out the end of the flume. While the velocity is increased, certainly the flow area at this cross section is smaller, and the product v times a is the same. So that's the continuity equation. It's a very commonly used equation that allows us to evaluate changes at different conditions, different locations down the channel. Another common equation in open channel flow that we use often, particularly for storm drain design, is the energy equation. We all had in high school the idea of two types of energy. We talked about potential energy and kinetic energy. remembering that the potential energy is the energy due to position, kinetic energy is the energy due to motion. In hydraulics, we refer to those terms as, for the potential energy, we refer to the elevation head, which is the elevation of the channel from some datum. We have the pressure head, which is potential energy due to the depth of flow. And then we have the velocity head, which is the energy due to the motion. The sum of all three components of energy defines the total energy grade line at that cross section. And what the energy equation says, the energy at section 1 should equal the energy at some downstream section 2 plus the intervening head loss. Well, we can demonstrate that energy concept with the flume by creating some varied flow conditions. I'm going to put the sluice gate down to create some head in the head box. I'm also going to increase the flow to make this a little more apparent. So now we've basically doubled the discharge. I'll put a little more slope on my flume so you can see a change in the elevation head. The pressure head in open channel flow is simply the depth of flow, and it's fairly constant down the flume, with the exception of what's happening here at the headwater. So we can kind of visualize the elevation head, we can visualize the pressure head. Well, what about the velocity head? We're going to look at that with something called a pitot tube, which basically will convert that kinetic energy into a potential energy that we can see. This is the same concept as what is on the nose of an airplane to measure airspeed. So if I put the pitot tube in just below my sluice gate, and I'll make a mark with my red marker, we see quite a bit of velocity head. In fact, the velocity head is the distance from the water surface to the rise in the pitot tube. Now, if I go to the end of the flume here, and I stick the pitot tube in, the velocity head is quite a bit lower. In fact, it's almost half as much. What you're actually seeing between those two positions is the head loss. We're seeing the slope of the energy grade line. Remembering that the energy grade line is the sum of the elevation head, the pressure head, and the velocity head. That energy loss is due to friction. Now, when I first did this experiment, I was a little bit surprised because I have a very smooth boundary channel. You wouldn't expect much friction loss. But as you can see, we had quite a bit of energy loss showing up in the pitot tube. Let's compare that to the form loss we might have up here at the sluice gate. So if I measure first the velocity head in the head box, well, there's hardly any rise at all. And that's kind of what we expect, because in a ponded water condition, there's not much velocity. So therefore, the velocity head, v squared over 2g, is very small. That's why sometimes in a ponded water condition, we make the assumption that the hydraulic grade line, which is the energy grade line minus the velocity head, is exactly or nearly exactly the same as the energy grade line. So in this case, my energy grade line and my hydraulic grade line are basically about the depth of ponded water. If I come down here with my pitot tube, I see an energy grade line, and I'll move this over so we can transpose the mark, is pretty high. There's not much difference in the energy grade line between the head box and immediately downstream of the sluice. We call that type of loss a form loss. A form loss is basically when water goes through a structure, changes direction, anytime there's some type of turbulence perhaps created in the flow environment, there'll be some kind of a form loss, in contrast to the loss we had initially, which was friction loss. And you saw how much energy loss there was with the friction loss compared to a fairly small amount, fairly small drop here due to the form loss. And that's pretty common. Years ago, we used to talk about major losses and minor losses. And the minor losses were the form losses because they really weren't very significant compared to the major loss in a storm drain, which is the friction loss. So that's a quick overview of the energy equation. The energy grade line is a sum of all the energy in the system, the potential energy plus the kinetic energy. The hydraulic grade line is below the energy grade line by the velocity head. Or another way to think about that, it's simply the sum of the elevation head and pressure head, the potential energy terms. So in my open channel here, where we had a sloping HGL, so we had an HGL that you can actually visualize, which is what's kind of nice about doing the flume here. You can see what the HGL means. Sloping downstream and dropping quite a bit, reflecting the friction loss. Between these same two sections, the hydraulic grade line doesn't change nearly so much. In fact, it's simply the water surface, and it'll, since we're pretty close to steady uniform flow, be the same as the bed slope. So the differences in the hydraulic grade line, which is something we often plot on our storm drain plans, is important because what it represents is how high the water might rise above the top of the conduit if it goes under pressure. That pressure head reflects the rise in, say, a standpipe. So what is a standpipe in application? Well, it'd be our catch basins, water coming up in those. It might be the access hole. It might be the pipes connecting to the catch basin. If we have a conduit under pressure, that HGL will rise up, and if it rises too high, water in fact starts coming out of our storm drain system instead of going in. So the energy equation is how we evaluate that, and in particular, we pay attention to what the hydraulic grade line is doing. The next equation we're going to look at, and I'll slow the flume back down for this, is the Weir equation. The Weir equation is used to evaluate, for example, flow conditions over a roadway embankment. This is in fact very similar to a broad-crested weir. In the highway engineering business, it looks like a roadway embankment, so we can use the Weir equation to evaluate the overtopping that would occur during a flood. The Weir equation says the discharge Q is equal to the coefficient of discharge for the weir times the length of the weir crest times the head H acting on that weir to the 3/2 power. So let me put the weir, the broad-crested weir, into the flume, and we'll see what the flow conditions look like, and we'll talk about the variables in the equation. Before we get into the equation itself, this gives us an opportunity to introduce the idea of subcritical and supercritical flow. With the weir in the flume now, we have water backing up upstream of the weir in a subcritical flow condition. Subcritical is when the Froude number is less than 1. The flow is very deep, flowing slowly. Another word for subcritical flow is tranquil, because that describes the flow condition we have. In contrast, at the other end of the weir, we have supercritical flow. The flow is very shallow and very fast. The Froude number would be greater than 1. An alternate word for supercritical flow is rapid. So a broad-crested weir creates two flow regimes. Upstream we would have subcritical flow, downstream supercritical, and in between we would pass through the critical depth, typically on the weir crest very near the leading edge. So now let's look at the Weir equation itself. Q is equal to the coefficient of discharge times the length of the weir times the head acting on the weir to the 3/2 power. The length of the weir is sometimes confusing. It's not the length in the downstream direction with my broad-crested weir, but rather it's the length across the weir crest. It's the width or the length of that weir crest that we're looking for in that equation. The way I keep that straight is if we had a 1-foot weir and a 10-foot weir, the 10-foot weir crest would clearly be passing quite a bit more flow. So in the flume, my weir crest would be 6 inches or 0.5 feet. The head acting on the weir is the difference between the upstream water surface and the height of the weir crest. So as flowing at the moment, the H value is about an inch. It's not very much. And it's measured a little bit upstream of the weir crest to get away from the drawdown as we go over the top of the weir. We can apply the equation, and we do this a lot in our training course classes. Take these measurements, we apply the equation, and it's actually quite remarkable using a C sub D of 3. You can look up a C sub D value for different weir types, and for a broad-crested weir, 3 is a reasonably good estimate. There's a small range on that number depending on conditions on the weir crest and submergence, but 3 is a good place to start. When we do that, we get a discharge that's very close to the known pump discharge that I'm running right now, which is about 0.05 CFS. So again, the broad-crested weir in the highway application gives us an opportunity to calculate the overtopping flow during a flood event, the amount of water that's going over a roadway. We also have the weir equation as part of many of the other calculations we do in highway drainage design. For example, a grate inlet in a sump acts like a weir at lower flow conditions. A curb open inlet on grade is like a side discharge weir. So this weir equation is integral to many of the drainage calculations that we do. There are other weir types, of course, and I've got a couple others I can show you. This is a sharp-crested weir, clearly because it has a sharp edge. We'll look at the hydraulic conditions of this weir, and then if I were to turn this over, we call this, in part because we're engineers and scientists and designers and we're not terribly creative. You know, if you go back to high school and you think about where you excelled, you probably did quite well in physics and math and chemistry and maybe struggled a little bit with English, composition, writing. So if this is a sharp-crested weir, what do you think we call this? This would be a not sharp-crested weir. Just, you know, remember, we're engineers and scientists here. So let's look at the sharp-crested weir first. And a characteristic of the sharp-crested weir is that the nap, which is the water surface coming over the top of the weir crest, springs up away from the weir crest. And I'll draw that here. But it looks something like that. Pretty typical of a sharp-crested weir. In contrast, if I turn the weir over to the not sharp-crested weir orientation, the flow either goes straight off the end of the weir or even tends to dribble down the weir. You don't see the springing of the nap. It's the same equation for all 3 weirs, it's just a different coefficient of discharge. So the weir equation, it's important in highway drainage design because it impacts and is underlying many of the calculations we do. We might apply it directly when we're looking at the overtopping conditions, say after a flood, how much water was going over the top of our roadway. But it's also part of our, say, a culvert analysis and inlet control before the culvert starts to seal off, before we get ponding at the upstream side. It's kind of acting like a weir. It's part of our grate inlet designs. So it underlies many of the calculations we do. The final equation we're going to look at is the orifice equation. The orifice equation says that the discharge Q is equal to the coefficient of discharge, which is not the same as the coefficient of discharge in the Weir equation. It's for the orifice equation, times the area of the orifice times the square root of 2g delta h. The orifice equation can be demonstrated in my flume using both a square-edged orifice, and then I have another orifice that's a rounded orifice, which is exactly the same diameter, the same area, at the same location. So I can slide the rounded orifice in front of my square-edged, and we can compare the differences in the headwater, the energy required to put the flow through that orifice opening. So let's start with the square-edged orifice. And what we'll be looking at is the amount of headwater required to push flow through the orifice opening. One characteristic of an orifice, particularly a square-edged orifice, is the diameter of the jet contracts coming through the opening. So the jet itself is quite a bit smaller than the area of the orifice. I'll mark the headwater on my stilling well. And then what I'm going to do is slide the rounded orifice in front of the square-edged orifice. So we'll be changing the entrance condition once my headwater stabilizes. We'll look at the drop in the headwater, and we'll also look at the change in the jet coming through the orifice. So here's the rounded orifice, and we immediately notice that the jet is now practically, if not identically, the same as the area of the orifice opening. And my headwater has dropped already. Now I haven't changed the discharge on the flume. I'm running about 0.05 CFS. So what that says is it takes less energy, less head to pass the same Q, the same discharge when I have a rounded orifice. If we look at the jet diameter again, you can see part of the reason that that's occurring. If I pull the rounded orifice out, that jet immediately contracts, and we're not making full use of that area. As soon as I put the rounded orifice in place, the jet expands to nearly the opening of the area, and the headwater's lower. So the orifice equation is an equation we use that underlies many of the calculations we do. For example, when a culvert starts to pond and we get headwater acting on the barrel, it's basically acting like an orifice. If we have a great inlet, for example, in a sump condition, we have water ponding above that opening, and it sees that mostly as kind of a horizontal orifice. The equation underlies many of the calculations we do in highway drainage design. This, in particular, this demonstration illustrates why it's important to think about the entrances to a culvert. That's why we at times want to bevel the head wall of our culvert entrances, because it can affect the headwater as it enters into the barrel. So the orifice equation, it's a common equation used in highway drainage design. I hope this review of basic hydraulic and open channel flow concepts has been helpful. If you have further questions or need additional information, you can refer to Hydraulic Design Series number 4, Introduction to Highway Hydraulics by the Federal Highway Administration, or the accompanying training course, NHI course 135065. Thank you for your interest in Federal Highway Administration training.